record on this. There you go. Okay. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, February 25, 2022. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a snowbound evening in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I am grateful for the continuing interest and support shown by members of the Rockport Research Explorers, Cape Ann Cultural Colleagues, cohorts of the Gloucester Area Astronomy Club, sundry science associates, far-flung friends, family, and other curious folk. Thank you for participating. This evening, I am pleased to be hosting Dr. John Ebel, who will talk about earthquakes in New England. John is a professor of geophysics at Boston College, as well as a senior research scientist at the Weston Observatory of Boston College. He has an AB degree in physics from Harvard and a PhD degree from the California Institute of Technology. His research interests are in the areas of earthquake hazards, earthquake source mechanisms, and earthquake forecasting, as well as seismic wave propagation studies and their application to the determination of the Earth's internal structure. In addition, he supervises the New England Seismic Network operations of the Western Observatory at Boston College. His own research focuses on studying the causes and effects of earthquakes in New England and vicinity. His research on earthquake activity in New England, as well as other seismically active sites in the United States, Canada, Mexico, and the Southwest Pacific, has resulted in 2 books, more than 80 scientific papers, 150 professional talks, and numerous technical reports submitted to government agencies and private firms. So we're most fortunate to be hosting you this evening, John. Let's get to it. The Zoom platform is all yours.
Thank you very much for that nice introduction. Let me bring up my PowerPoint, and I trust you all can see that.
Good.
That out of my way. And I'm going to be talking about earthquakes in New England. What I've got here on the right-hand side of the screen is the cover of my second book, entitled New England Earthquakes, The Surprising History of Seismic Activity in the Northeast. If you're interested in a copy of that book, it's available if you just get onto Amazon or Google my name and earthquakes in New England, it will pop right up. And the book is really, it starts with a tutorial on earthquakes in general, and then has a number of chapters, each chapter describing a different historical earthquake that has occurred, or even recent earthquake, because the most recent earthquake is 1988 in the book. And there are lots of descriptions, past descriptions from historical documents, newspapers, scientific reports, things like that. And so it really gives you a feeling for what the history of the seismic activity of New England is. I'll summarize a little bit of the information in that in the book as I go through my presentation. So we're going to begin by talking about what an earthquake is. So if we have a block of rock, that block of rock is under pressure. And those pressures arise due to the movement of the tectonic plates over the surface of the Earth. And those pressures, in some cases, squeeze the rock, in some cases, extend the rock. What I've shown here is a case where the rock is being squeezed. Now, if you think about a clay brick and you put it in a vise and you start cranking the vise and closing the vise, increasing the pressure on the brick cannot withstand that pressure forever. Sooner or later, the pressure gets high enough that the brick will crack and break. And that's literally what is happening in the Earth when we have an the earth crack and an earthquake occurs. The cracking is simply to relieve the pressure that's on the rock. And when the rock cracks, that crack is a feature in the rock that we can find, a year after the crack, 100 years after the crack, 1,000 years, 1,000,000 years, even 1,000,000,000 years after the crack, because unlike skin, rock does not heal. So the crack is shown here. And when the crack occurs, the sliding of the rock releases vibrational waves. And that's what we feel as the earthquake shaking. Technically, we call them seismic waves. So when you feel an earthquake, you are feeling the waves that have been released by some sort of a movement of the rock inside the earth. The crack starts at a single point, just as if, you have a rock hit your windshield when you're driving, and that starts a crack, and the crack grows away from where the rock impinges on the windshield itself. Well, the place where the crack starts in the earth has the name of the earthquake focus. And if you project the position of the earthquake focus directly upward to the surface of the earth, that gets you to a spot that's called the earthquake epicenter. So when you hear, the epicenter of the earthquake was at a certain place, in fact, the focus of the earthquake was below, but usually the press doesn't tell you how far below, whether it's 1 mile or 10 miles or 100 miles. Now, the crack that has the movement during the earthquake has the name of an earthquake fault. People these days like to use the term fault line, but a fault is not a line. It's actually a surface in the earth upon which you've had movement. If you look at, if you draw where the fault intersects on the surface on a map, then you would draw the intersection of the fault on the map as a line. And I think that's where this false notion of a fault line comes from. But you can see that in the drawing here, the rock layer on the one side of the fault has been pushed upward. On the left side of the fault, on the right side of the fault, it's been pushed downward, and the arrows indicate that. And that's actually what we do observe on faults after earthquakes have occurred. The rock layers have been shifted in the manner shown here. Okay, so earthquakes take place all throughout the world. And you just watch the press long enough and you realize this. This is a map of earthquakes of the order of 30 years. These are magnitude greater than 5 earthquakes. And you can see that there are linear belts of earthquakes. Sometimes they're broad belts, sometimes they're very narrow belts that span the earth. Some of them run into the oceans. You can see that there's a belt of earthquakes that runs down the center of the Atlantic Ocean. There are belts, for instance, along the west coast of South America, Central America, and North America, Alaska, and down through the Aleutian Islands, and then many belts in other parts of the world. Those earthquakes are taking place at the places where we have plate boundaries, where 2 tectonic plates are somehow moving and rubbing together. Either they're pushing together, or they're sliding past each other, or they're trying to pull apart. Now, about 90% of the world's earthquakes take place at plate boundaries. However, about 10% of the world's earthquakes take place in the middle of the plates, away from the plate boundaries. We here in New England are actually in the middle of a plate. One side of the plate is in California and Oregon and Washington, but the other side is in the center of the Atlantic Ocean. So even though we're at the edge of the continent, we're actually at the center of a plate. So here's a map for the year 1996, and it just happens to be a nice map that I found that illustrates what I wanted to show. And what you can see is most of the earthquakes that were recorded in North America in that time period of 1996 were along the West Coast. Most, in fact, show up in California and then offshore Oregon, and then you see a few under Oregon and Washington, and then there are some scattered kind of in general in the Rocky Mountain region. And then there are a few earthquakes in the central and eastern part of the country. Now, people say, well, the earthquakes are different in New England than they are in California. And I did my PhD at Caltech, so I studied California earthquakes. And then I came to New England. I started studying New England earthquakes. And to me, an earthquake is an earthquake. The earthquakes here in the East look just like the earthquakes in California, but there is a difference. And the difference is not in the sizes or anything like that. It's in the rate at which earthquakes occur. If you go to California and do seismic monitoring and count the number of earthquakes that you get in 1 year, come to New England, do the same kind of seismic monitoring, count the number of earthquakes that you get each year, you would have to wait between 100 and 150 years to get the same number of earthquakes recorded in New England that you get in 1 year in California. That's really the difference. They have a much higher rate of earthquake activity by a factor of about 100. Otherwise, there are small earthquakes in California. There are occasional large, very occasional damaging earthquakes in California. Same thing is true here. Most of the earthquakes are small, some somewhat larger, and a very, very, very occasional damaging earthquake, about 100 times less frequently than in California. There's one important difference, though, between the earthquakes in California and the earthquakes east of the Rocky Mountains that is important to understand. What we're showing here is plots of some earthquakes. You notice that the 1906 San Francisco earthquake and the 1971 San Fernando earthquake are shown in California. And there's two zones that's shown. The dark gray zone shows where the damaging earthquake shaking occurred, and then the hatched zone shows the areas where there was strong earthquake shaking, but only maybe a little bit of damage might have occurred in those areas. Then on the right are two plots of earthquakes for the eastern part of North America. One is the 1811 earthquake in the New Madrid seismic zone, southern Missouri. The other is the 1886 Charleston, South Carolina earthquake. The New Madrid earthquake was probably about 7.5, 7.6, roughly comparable to the magnitude 7.8 earthquake out in San Francisco. The San Fernando earthquake was about magnitude 6.8, Charleston earthquake about magnitude 7. And what I want you to notice is how much larger both the damage areas and even the areas of minor or potential minor damage are for these eastern earthquakes than for the earthquakes in California. So even though our earthquakes are less frequent, when our earthquakes do occur, they have the potential for causing damage over a wider area. So the city of Los Angeles, which is in California, experiences about 100 times more earthquakes than we do in the greater Boston area. But an earthquake much farther from Boston has the potential for causing damage than does an earthquake at that same distance from Los Angeles. So what we call the seismic hazard, or the potential for damage in any given year in Boston, is only about 30 times less than the potential for damage in Los Angeles. So that's something to keep in mind. Yes, the earthquake rate is 100 or 150 times less, but the potential for damage is only 30 times less in Boston than in Los Angeles. So what causes our earthquakes? Well, go back to the first slide that I showed you. The earthquakes are caused by the pressure due to the movement of the plates. So here we have a drawing of the plate boundaries around North America and South America. And what you see is arrows that show the motions at the different plate boundaries of one plate relative to the other. So North America is spreading away from the Eurasian plate and the African plate. And as it does so, it's pushing toward the west, and it's pushing up against the Pacific Ocean plate. Now you have to understand, you're looking at a flat map here, but this is really representing the plate on a globe. And plates, as they move on a globe, actually rotate over the surface. And so the rotation pull for North America in this particular plot is somewhere down in the Caribbean, basically somewhere in the area of eastern Cuba. And so that rotation causes the motion of the North American plate near the mid-Atlantic ridge to be toward the northwest. In the area where we are, that rotation motion causes our local plate motion to appear to be roughly toward the southwest. And by the time you get to California, that rotation causes the plate motion to appear to be almost due north-south, just slightly east of due north-south. Now, what this means is because we're spreading in the east, away from Europe and Africa, and we're hitting a collision to the west, North America is being caught basically in a vice. It's being compressed. And so what this is doing is this is causing the rock to be compressed in northeastern North America in a roughly east-northeast, west-southwest direction. And it turns out we can actually verify that with observations that we make from the seismic waves of the earthquakes that we record. So this is actually a very, very rigorous and robust observation. Let's talk about earthquake magnitude. Now, the magnitude scale was developed. I know some of you are interested in astronomy. It was developed by the seismologist Charles Richter at Caltech. Turns out when I was a brand new graduate student at Caltech, I was assigned to read seismograms in our seismogram reading room. And in those days, of course, all seismic recordings were on paper. And I was there with the woman, Vi Taylor, who was in charge of the room. And in walks this man with a suit on and tie on. And Vi says, "Oh, John, I would like to introduce you to Dr. Charles Richter." And it was indeed the Richter of the Richter scale. And he was a professor emeritus at Caltech when I was there. Rick came up with the magnitude scale. And when he did so, he took a bunch of measurements of earthquakes and was plotting the sizes as a function of distance from the epicenter and was extrapolating back to the sizes of the earthquakes near the epicenter themselves. And then he wanted to assign some number to the size of the earthquake. Well, Richter turns out to have been an amateur astronomer. And so he said, well, you know, sizes or brightnesses of stars are measured on a magnitude scale. So he said, I'm going to use the same word for sizes of earthquakes. And just as the astronomical magnitude scale is a logarithmic scale, so he made the earthquake magnitude scale logarithmic. He adjusted the numbers, though, whereas astronomers have negative numbers for the magnitudes of stars. He adjusted the magnitude scale for earthquakes such that the smallest earthquake that could possibly recorded would be around magnitude 0 or so, maybe a little bit less, maybe a little bit more. And the largest earthquake that could be recorded would be roughly in the magnitude 10 range. In fact, on Richter's scale, the smallest earthquakes that typically are felt are around magnitude 2. Damage starts around magnitude 5 right at the epicenter. By the time you get to magnitude 6, now the damage is stronger at the epicenter and spread over a wide area, magnitude 7, even more damage in the epicentral area, and the damage areas spread much wider also. And I just put on here the largest earthquake ever recorded, because that's a common question people ask. It's 9.5. That earthquake was in Chile in the year 1960. So here's a map of the earthquakes either known from modern seismic measurements or suspected from estimates from looking at historical accounts and comparing them to the modern earthquakes, of all earthquakes of magnitude 5 or greater. So in other words, all earthquakes that were either damaging or had the potential for being damaging known historically. Earliest earthquake on here is 1638. And as you know, the Pilgrims landed in 1620. So that was only 18 years later when they felt their first earthquake. The largest earthquake on here is probably the earthquake that was centered in what we call the Charlevois seismic zone. So you see it right at the top of this plot. And that was in the year 1663. That earthquake was strong enough that it actually damaged some chimneys in Roxbury, Massachusetts at a distance of 400 miles. My estimate of the magnitude of this earthquake is that it was around magnitude 7.5. Certainly it was easily above magnitude 7. So it was a strong earthquake. And I'll talk a little bit more about that earthquake later. But you can see that there are earthquakes in New Brunswick, Maine, New Hampshire, Massachusetts, New York State, New Jersey, Quebec province, Ontario province. So we do have earthquakes that have been damaging, that have been spread broadly throughout the region. So here's a blow up of the earthquake activity for 26 or so years in the area, and I'll go back to the previous slide, in the area of this Charlevoix seismic zone. And you'll notice all the stars up here, all the earthquakes greater than magnitude 5 that have occurred since 1663. Very active zone. In fact, that is the most seismically active zone here in the Northeast, and is comparable in activities, a rate of activity to the New Madrid seismic zone of that had the big earthquakes in 1811 and 1812. In fact, I think the 1663 earthquake was comparable to the largest of those New Madrid earthquakes. So this is a very, very significant seismic zone. You can see that there are lots and lots of earthquakes that were mapped over this 26-year period, and they cover a trend parallel to the St. Lawrence River, and the trend is about 70 kilometers long. Now, there was a paper published by a couple of seismologists, Youngs and Coppersmith, in 1994, that looked at worldwide earthquakes and said, well, if the earthquake has a fault length that's longer than about 70 kilometers, that puts it in the magnitude 7.1 to 7.5 range, which is consistent with the number that I actually inferred from other kinds of measurements. So this was clearly a very, very large earthquake that occurred in 1663. And I think that these are still aftershocks today of the 1663 earthquake, which now is, 350 or so years later. And in the areas of interplate regions, I think that the aftershocks can last, at least at some low level, for a very, very, very long period of time, hundreds to perhaps even thousands of years. For us here in New England, and particularly if you happen to live in a place like, for instance, Cape Ann, the earthquake that occurred in November of 1775 is one that you need to know about.
1775.
The 1755, this is called the 1755 Cape Ann earthquake. It was November 18th, 1755. It turns out it was 18 days after the great 1755 earthquake that did major damage in Lisbon, Portugal. And whether or not there's some connection, I don't know, but that's something I've always been curious about. And what you see here are some dashed lines on the map of New England. And those dashed lines show areas of strength of shaking, with the strongest shaking in the innermost dashed line, weaker and weaker shaking as you're going out. This earthquake was felt up to Nova Scotia, and it was reportedly felt to South Carolina. It was certainly felt at least to the northernmost part of the state of New York on Lake George. And we know that it was felt in Maryland. And the epicenter is thought to be offshore. There was damage, a lot of damage in Boston. About a third of the chimneys were damaged in Boston. Brick is very brittle, so it's very easy to crack brick buildings. Wood frame structures, like our typical wood frame house, bends, and it tends not to break or crack in earthquakes very much. However, if you have a house with a chimney, now you have this stiff chimney, you have this bendable house, and the house actually beats on the chimney and cracks the chimney. So one would expect brick chimneys were damaged, brick walls were damaged, the tower atop Faneuil Hall was damaged in the earthquake. There was damage in Portland, Maine, Portsmouth, New Hampshire, down in the town south of Boston, going to the western suburbs of Boston. And that seems to have been about the limit of the chimney damage. Based on where the damage was experienced, Seismologists favor putting the earthquake offshore. And that's where I favor the epicenter also. And I'll show you some evidence later as to exactly where the epicenter probably was, but it was of the order of about 30 miles east of Cape Ann. Based on the area over which this earthquake was felt and over which it caused damage, and comparing that to the areas to modern earthquakes that have occurred in the areas of damage and felt effects, I think that the 1755 earthquake was about a magnitude 6.25 earthquake. There was a somewhat smaller earthquake, but still significant earthquake that occurred in Newburyport, or the Newburyport, Amesbury area in 1727. So you're talking about prior to the 1755 earthquake. The 1727 earthquake was felt and caused some damage in Newburyport, Amesbury area. It was felt strongly in Boston, but there's no damage that I have ever found reported. Felt through Rhode Island, Connecticut, Massachusetts, down to New York City. And there was a report of the earthquake being felt at a very small level in Philadelphia. Based on the area of where this earthquake was felt, my estimate of the magnitude is about 5.6. You notice that there are not a lot of reports inland, and that's because there were relatively few settlements inland, and they just didn't seem to preserve the record of this earthquake. One of the interesting things about this earthquake was that it was followed by a very vigorous and protracted aftershock sequence. Now, the earthquake occurred on October 29th of 1727, occurred about 10:30 in the evening. So 2 days before the end of the month. And what I've got done here is I've gone through a lot of records, diaries, town histories, church records. Turns out there was a minister in the Newbury area who kept a record for months and months and months of every aftershock that he felt. So we get quite a good record of the aftershock activity. So there's a bar chart here with numbers. So you notice the first bar has 25, second bar has 53, third bar has 7, fourth bar has 19, etc., going all the way out to 1735. Those numbers are the numbers of aftershocks felt each month in the Newburyport, Amesbury area after immediately following the 1727 earthquake. Look at the month of November 1727, 53 earthquakes. Can you imagine living up near Newburyport and feeling 2 earthquakes per day for a month? But that's what they did. There were 25 earthquakes that they felt just in the 2 days plus a couple hours following the main shock on October 29th. Now, there are arrows there with numbers, and I have to go back to the previous slide. Dedham, Massachusetts, there's a Roman numeral 5 here, which is an indication of the strength of the shaking on an intensity scale. And that's at Dedham, Massachusetts. And for an earthquake to be felt at Dedham, Massachusetts, it had to have been around magnitude 3.7 to 4.0. And these arrows here show the number of earthquakes felt at Dedham, Massachusetts, and earthquakes that were felt at times that correlate exactly with times of earthquakes were felt up in the Newburyport area. So in the 2 days plus a little bit following the main shock, they felt 8 aftershocks in Dedham. 1 in November 1727, 1 in December 1727, 2 in January 1728, etc. So you can see that not only was there a very protracted set of aftershocks, but 17 of those aftershocks were probably magnitude 4 or greater. Maybe not large enough to cause damaging, but if you feel a magnitude 4 and you're near the epicenter, it gives you a good scary shake. So we do have aftershocks and protracted aftershock sequences from some of our earthquakes here in New England. And if I were to show you the aftershock pattern of modern earthquakes, it would look very similar to this.
John, are you taking questions?
I can take a question if you want.
What's the difference between an aftershock and an earthquake? especially if the aftershock is years after the original earthquake. How do you determine that?
Well, the term aftershock is really a semantic term, and different seismologists would interpret that term in different ways. Aftershocks are earthquakes. The seismograms look just like any other earthquake, but just the numbers of earthquakes are way beyond what we normally observe. So we use the term after.
Okay, thanks.
Where you might have an earthquake felt every 5 years, Newbury, and suddenly you're getting, 25 earthquakes in 2 days and 53 earthquakes in a month. That's clearly way, 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 way out of normal. And that's why we call those aftershocks. And aftershocks happen after all big earthquakes anywhere on the globe. There was an earthquake in the New York City area that was around magnitude 5 that took place in 1884. You could read descriptions of it in my book. You can see that earthquake was felt up to at least Portland, Maine to the north, out to Cleveland on the east, felt down past Washington, D.C., into northern Virginia. I think it was probably felt at Richmond, Virginia. And it did some minor damage in the greater New York City area. Estimated to be around magnitude 5, so right at the threshold for damage. So you can see that in the last example, I showed you an earthquake that was damaging in Boston. Here we have an example of an earthquake damaging in New York City. There was an earthquake that was very interesting in 1929. We call it the Grand Banks earthquake. And this earthquake was centered in the rock beneath the Grand Banks, south of Newfoundland and east of Nova Scotia. Occurred on November 18th, 1929. Notice that was the same date of the 1755 earthquake. Just a coincidence, but an interesting coincidence nonetheless. The 1929 Grand Banks earthquake caused a tsunami in the Atlantic Ocean. And the tsunami was so great in southern Newfoundland that it inundated fishing villages along the coast of southern Newfoundland, and I've seen numbers anywhere from 25, I think, to 44 people, but it was probably in the upper 20s of people who were killed by that. They call it a tidal wave here, but it's really a tsunami, and literally people were pulled out into the water and drowned, and in many cases the bodies were never recovered. The earthquake itself the shaking from the earthquake was felt all throughout New England. You can see that in the Roman numeral 3 here was felt in Boston. Roman numeral 3 means that the shaking was mild but noticeable. Most people would have noticed that earthquake. It was felt all the way to New York City. There are a number of dots on this map. The star shows where we think the epicenter was, but the dots show places where transatlantic telephone cables were crossing the ocean, carrying telephone signals from North America over to Europe. And there must have been a big submarine land slump triggered, or slump of sediments triggered by the earthquake. And that slump evidently broke a number of these submarine cables here. So the telephone cables actually had to be repaired, and they would go out and fish the cables up, find out where they broke, fish the cable up on the other side, and then they would have to patch them together again. So that's how they know exactly where the cable breaks were. So there was obviously a major submarine slump associated with this magnitude 7.2 earthquake, and it's likely that submarine slump is what caused the tsunami. Now, what's interesting to me is if we can have a tsunami there, I see no reason why we couldn't have a similar kind of large earthquake and submarine slump, say just east of Boston, and give us a tsunami along the New England coast, as well as happen in Newfoundland. So we actually do have some hazard of tsunamis here in northeastern North America. Here's a map of earthquakes. Because of COVID, we haven't updated this map in a long time. So I grabbed one that was available, and this is from 2016. And this shows the earthquake activity that's been detected by good monitoring seismic stations, which started to be installed in the mid-1970s. So these are all good locations. They're good magnitudes. If they're stars, that means they're above magnitude 5. The size of the symbol is related to the magnitude. And what I want to do is I want to point out to you a couple things. The first thing is that there are earthquakes that scatter all throughout the region. So it's not like you can say, oh, well, there's one place and there's one fault and that's all we have to worry about. Earthquakes are everywhere. And my personal opinion is any place that we have a small earthquake today or tomorrow or had one yesterday could be a location of a potentially damaging earthquake in the future. So an earthquake of magnitude 5 or greater sometime in the future. So that's the first thing I want to point out to you. You can see that the magnitude 5s are scattered all throughout the region. So there's no one spot where a magnitude 5 earthquake is centered. Largest earthquake since this map was made was in 1988 up here at the Charlevoix region of Quebec province. This 1988 earthquake, as well as an earthquake here at this star 1982, those are actually described in my book. This 1982 earthquake actually caused a little bit of damage in Maine, up in the Caribou area. So you can see that earthquake activity is broadly scattered throughout the region, but at the same time, you can see that there are some places where there's greater scatters of earthquakes. For instance, here's the Charlevoix seismic zone. Lots of scattering of earthquakes here in Western Quebec and into Ontario province. You notice patches in Maine, patches in New Hampshire, offshore. If you look right here, east of Cape Ann, that there's a patch of earthquakes. I think these earthquakes east of Cape Ann are aftershocks of the 1755 Cape Ann earthquake. And I think these small aftershocks east of Cape Ann are showing us where that 1755 earthquake was epicentered. And that's where people had guessed the epicenter based on where the earthquake was felt and where the damage was long before we had a map like this. So I think perhaps a lot of these clusters of earthquakes that we see could potentially be aftershocks of earthquakes that occurred hundreds, maybe even thousands of years ago, a few thousand years ago. Final thing I'll point out on the map are look at all of the clusters of earthquakes offshore. Again, thinking back to the 1929 earthquake, I think this is evidence that what happened in the Grand Banks in 1929 could potentially happen along, say, the New England coast south of Nova Scotia, or the New York, New Jersey coast east of New Jersey and south of Long Island. Now, one of the things that we can do with small earthquakes is plot the number of earthquakes at different magnitudes. And the small earthquakes are most frequent, large earthquakes are a little bit less frequent, larger earthquakes still a little bit less frequent. So if we know the time period over which we do this plot, we can actually extrapolate it to much longer, larger magnitudes than is actually in the data set itself. So the data set on this previous slide goes up to magnitude 5.9. Well, we can extrapolate the data to magnitude 6, even to magnitude 7. And using those data, we can get estimates of what I think are the mean repeat times of earthquakes of magnitude 5 or greater. So damaging earthquakes. And these are New England earthquake probabilities. These are probabilities of an earthquake centered in New England itself. So magnitude 5 or greater is every 60 to 94 years. 6 or greater, 447 to 1,000 years. 7, 4,500 years to 11,000 years. Last earthquake of magnitude 5 or greater was in 1940, centered in New England itself. Magnitude 6 is 1755. Magnitude 7, we don't know. We have no evidence, direct evidence to tell us when those larger earthquakes, when an earthquake of that size may have occurred. But you can see that if we had another magnitude 5 or greater tomorrow, that wouldn't surprise me at all, because we would just be catching up with the long-term statistics. When we get to smaller magnitudes, a magnitude 4 or greater earthquake occurs once every roughly half a decade in New England on average. Magnitude 3 is about a twice a year earthquake. Magnitude 2 occurs about once a month somewhere in New England. So earthquakes are frequent, and the rate of earthquakes has varied some over the decades, but not very much. Now, what would happen if an earthquake were to occur in New England itself? And that's really what I want to finish up with. There was a study that was done in 2012. I was one of the authors on it. You'll notice my name is on here in the lower right with Weston Observatory. And what we did was we took a bunch of different earthquake scenarios, estimated what the earthquake shaking would be, the pattern of earthquake shaking in different parts of the region, and then estimated how much damage that shaking would cause. So in this scenario, we put a fault right in central New Hampshire, made the earthquake about magnitude 6.5. And the hotter the color, the stronger the ground shaking. So most of the damage would be in central and southern New Hampshire, but damage also in northeastern part of Massachusetts. Economic losses from this earthquake scenario estimated to be $8.3 billion, with perhaps 2,100 people injured and perhaps 80 people killed. Maybe 4,500 people would have lost their homes due to damage or fire or whatever. And right after the earthquake, probably you would have tens of thousands of people without power. And here are, I'm just going to skip this, but just to show you potable water, wastewater, natural gas, oil systems, electrical power, communication systems are all assessed in this particular study. Now, one of the things we know is that when you have a strong earthquake, the soils determine how strong the shaking is. So if you have really hard soil, you have a certain level of shaking. But if you have soft soil like mud or something, as is shown right here, the shaking actually gets amplified. It's actually stronger. So there was a freeway that in the 1989 earthquake out in the San Francisco Bay Area that came up through Oakland and then came up along the so-called East Bay Area here. And right when that freeway got onto some very soft muds, the shaking was very strong and the freeway actually collapsed. A number of people were killed in that structure. Once it was on the harder materials, then the freeway stayed up, but even though it got a good shake. And so what that says is, if you want to know how much damage you're going to have from an earthquake, you don't just need to know where the earthquake is and what its magnitude is or how far away you are. You also need to know what the soils are that you're built on. Now, that's interesting for Boston because here's a map of the Shawmut Peninsula of Boston. The white is the original Shawmut Peninsula when the Pilgrims first landed here. And you can see all the areas that have been filled in, the Back Bay, West Cove, Mill Pond, etc. 2/3, roughly, of the current area of downtown Boston is on filled land. And the problem is that filled land could amplify ground shaking. Here's another view. When you land at Logan Airport, you're landing on filled land. All of those filled land areas have the potential for amplifying the ground shaking more than you would if you were on, let's say, on Beacon Hill or over in Brookline, the hills of Brookline, areas where there's rock sticking up near the surface. And so here's some soil profiles for what those Boston soils are. A lot of marine deposits and organics, and then fill on top. And I'm going to skip these because these are a little technical. And I want to come to here. We actually did some simulations to see where the strongest ground shaking would be. And it turns out to be in the Back Bay. So the Back Bay will shake most strongly when we have a strong earthquake next in the region. Now, the shaking gets, there are some what we call nonlinear effects that can diminish the strength of the ground shaking a little bit if it's really strong. But still, the Back Bay is going to shake very, very strongly if we do have a strong earthquake. And other fill areas will shake strongly as well. And this shows a different analysis, really a different frequency of analysis, but the same kind of story holds. Now, what's interesting in the Back Bay is the strongest shaking is probably going to be at about 2 hertz, which preferentially would affect 5 to 10 story buildings. And the thing is, that's the size of the building that the buildings that you typically have in the Back Bay. So that also is a recipe for real problems in the Back Bay if we have a strong earthquake. So with that, I'm going to close my formal remarks. I'm happy to take questions, and thank you all for your attention. I'm going to stop sharing, but I can go back to sharing if we need to with the questions.
John, are these earthquakes from the Atlantic epicenter spreading area?
There are earthquakes out in the spreading area, or the spreading ridge is what we call it, between North America and Europe, or North America and Africa. Those earthquakes are confined to the center of the ocean. They are too far away to affect us here in on the onshore areas. Neither us here in New England or in North America, nor the people in Europe or Africa are affected by those earthquakes. All of the earthquakes I showed you right here, or showed you on the earlier slides, are earthquakes that are right near associated with the continent itself, with the land area, nothing to do with the center of the earthquakes at the center of the ocean.
Are they deep or shallow near us?
The earthquakes are what we would call shallow earthquakes. They are the shallowest earthquakes are maybe 1 kilometer deep, so like 0.6 of a mile deep. And the deepest earthquakes we've seen here in our region are about 30 kilometers deep, maybe a little bit deeper, so about 20 miles. The biggest earthquake that we've recorded since 1975, that 5.9 earthquake, was also one of the deepest earthquakes we've seen in New England. And that actually still has me puzzled even today.
I was more worried about the La Palma volcano eruption over in Cumbria volcano, because if that landmass slid into the water, we'd be up to our keisters.
Yeah, I'm not so worried about that. There was some modeling work that was done quite a number of years ago by a colleague that I know, Steve Ward, and he had a model where he had the volcano, a major side of the volcano slumping into the ocean, generating a tsunami that would travel across the ocean. And then they were talking about 100-foot waves in New York City and all this sort of thing. And the press really blew that up into a big story. People have more recently re-examined those calculations, and they think that they're just not right, that the waves would be much, much, much smaller from that any collapse that they would have there. There would be big tsunamis, obviously, in the Azores and the Canary Islands and islands off of Africa and Europe and the European coast itself. In the 1755 earthquake in Lisbon actually had a very damaging tsunami in Lisbon. That tsunami was probably experienced here in North America also, but the only direct observation we have is from down in, I think it was Bermuda, where they saw 3 feet of water rise from that tsunami.
John, I want to stay with local New England earthquakes for another second here. Actually, I have 2 questions. The first one is you talked early in the presentation about being able to see these sort of planar faults where things had slipped. How do you do that? What's the methodology? How's that happen? How do you look 10 miles deep?
So the first thing you do is you look at the surface, and geologists, if they go and they find a spot and the rock obviously has a crack in it, and you have one kind of rock on one side and a different kind of rock on the other side, the only way, well, maybe not the only way, but a very common way that happens is in a very old faulting event. And I mean, I'm talking about faulting events that might have been hundreds of millions of years ago. Sometimes you actually find the rock has cracked itself in a way, and then when it cracked and then slid, it leaves little scratch marks on the surface of the rock itself. The geologists have a fancy name for that. They call them slickensides. And so if you find a rock surface with slick sides, that indicates that that rock had fault movement at some point in the past. Now that's going on at the surface. What the geologists then do is they project the rock, they project the fault down to depth. And by looking at the geology, sometimes they can make an inference or a guess as to how deep that fault must go into the earth. And then the other thing that the geologists do is they rely on seismologists like myself to look for earthquakes. And if we can locate earthquakes and have them line up in a line going down to depth on a fault trend that's mapped at the surface, that's the best indication that we have, not just a fault, but a potentially active fault.
Okay, and all these little earthquakes around New England, every place there's been one of these, we now have a new fault?
Well, whenever you have an earthquake, you have two possibilities. Either it is an earthquake that occurred on an old fault that just slipped again, because we see, faults will slip many, many, many times. You have the San Andreas Fault, for example. It has slipped, probably 100,000 times or many, many, many thousands of times, such that the rock has been pushed 500 kilometers, 300 miles from where the rock started. And that's, an earthquake every 100 or 200 years. We see evidence of the slip of the faults, and can infer that there's been a number of slips in the past. The problem we have with New England is so many of the earthquakes that occur, if we have one earthquake occur in one spot, the geologist may or may not have mapped a fault there. And so tying the earthquakes to the faults can be very, very difficult. And then in the Los Angeles area in the 1980s, there was some earthquakes that occurred on faults that were not mapped geologically at the surface. And they call those blind thrust faults. And our earthquakes here in New England are thrust earthquakes. And so it's very possible we have many blind thrust faults in New England as well. So the association of earthquakes and faults is something I'm very interested in. I'm trying to figure out. But right now, it is really a very, very enigmatic puzzle.
All right. Very nice. Thank you.
We have two questions in the chat. The first from Christine Downing is whether there is an old volcano in Roxbury. Are there any tremors evident in the Roxbury area?
Okay, so let's talk about old volcanoes too. It depends upon what you mean by an old volcano.
Mm-hmm.
Any place that we have granite in New England, that granite is the cooled magma chamber of a volcano that was active. Now, the cooled volcanic rocks here are typically 350 million years old, 400 million years old, 450 million years old. There's granite that sticks up in Scituate. You have the granite of the Blue Hill. There's there's granite. Well, there's a lot of granite up on Cape Ann, for example.
Sure.
There's granite all throughout the area. And then of course you get up in New Hampshire and that's the granite state. So was there volcanism at one time? Oh, there is all kinds of evidence of volcanism at one time, but literally hundreds of millions of years old. Now, modern earthquakes, there have been earthquakes in the western suburbs of Boston. There have been earthquakes in the northern suburbs of Boston. I dealt last year. Many of you probably heard about or may remember, a little swarm of earthquakes in the Peabody area. There have been earthquakes south of Boston. You get down to Quincy and Dedham and places like that. But so far with, good seismic monitoring since 1975, so now we're approaching 50 years of good seismic monitoring, nothing under the central part of Boston itself. So nothing that I know of, say, in the Roxbury area,
Okay.
if you're to just take an area like that.
Here's the second question from Rick Davis. Do the tectonic plates rotate in the same direction everywhere on the globe?
No, but that's because they each are being pushed in a different way. So for instance, I don't know if I can show this or not. So if you have one plate moving in this direction, so I'll move my hand back. You have one plate moving in this direction and another plate rotating against it, you're going to have both a push and a slide by taking place at the same time. So in other words, one plate is rotating like this, one plate is rotating in a very different direction. And that's and then we see the plate boundary interactions. It's something like that in California, because if you get up to Oregon and Washington, now you actually have two pieces of plate coming together, because there's another little plate that's forming offshore that's pushing under North America. Used to be a much bigger plate. Now it's a really tiny plate. But every plate is rotating. In fact, one of the things that the people who study plate tectonics do is they actually, for each plate, they go and figure out where the so-called pole of rotation is. So if you're rotating, around a point, they find where that point is, and then they plot those on a map, the poles of rotation of the different plates, and they're scattered all over the place.
Well, I have a question with regard to insurance.
Yes.
Let's say you live in a granite house like I do. Should I be getting earthquake insurance?
Yeah, earthquake insurance is really a difficult question for me. And the reason why I say it's a difficult question for me is because earthquake insurance, like all insurance, is priced to make money for the insurance company.
Right.
And insurance companies love to collect premiums. They hate to make payouts. You might be interested to know, for instance, that most people in California do not have earthquake insurance. And the reason is very simple. So your typical house in California might be worth $800 million, or I'm sorry, $800,000 or $1 million. So let's just take 800,000 to make it easier. Let's take $1 million rather to make it easier.
Mm-hmm.
So if your house is worth $1 million, now you're going to pay a good premium for earthquake insurance, but the typical earthquake insurance policy in California has 20% deductible. So you are responsible for the first 20% of the damage, and then they will pay for everything above that. So if you have $1 million home, you have to come out with $200,000 out of your own pocket to pay for the repair of the damage before you even start collecting on the insurance. So they found there was an earthquake in 1994, and I saw a study that found that even though you had all these people who owned earthquake insurance, very few people collected any money at all, even though all these houses had damage because of the deductible. So what would take damage in a house in New England? It's very simple. Anything that is brittle. Your plaster walls are going to take cracks, and that will cost to be repaired. Your brick chimneys or stone chimneys are going to take damage. Now, if you have an old house and if you have brick walls on the house, those will probably take damage. I worry about foundations of old homes, particularly. I have a friend who used to own a home in Newton, and he took me down in his cellar. Round field stones, round cobblestones that were just cemented in place 150 years ago now, probably. And you shake those stones in a big earthquake, and I bet that the foundation of that house would take severe damage. And of course, you damage the foundation of the house. Doesn't matter what the house above is made of; it's going to take damage. So you look at the things that could take damage and assess whether or not it's worth it for you to buy the insurance to cover that damage. So for a lot of people, they say the earthquake insurance is really cheap. It's a rider of $30, $40 on my policy. So I buy it. Great, fine. So, if your chimney's damaged in the earthquake, you can get your chimney repaired, because that's where you're most likely going to take the damage. You can get the walls replastered and painted and things like that. But that's most likely what's going to happen. Most houses will not fall down. You're not going to have catastrophic damage.
Well, I think we have one last question from Dick Lukey. Some minor quakes have been attributed to fracking, human caused. Do you have any thoughts on that?
Well, let's see. How many hours do we have? No, yeah, I have many thoughts on that. The first thing to know of is we do not have the right geology in New England. There is no fracking anywhere in New England. The closest places that you get that sort of activity, you could have it in New York State, but I think it's outlawed there. So you have to go down into Pennsylvania before you get into that, into the fracking and the production of oil and natural gas using the fracking technique. The evidence is unquestionable. There are places where fracking activities have induced earthquakes. Now, in most cases, the activities are not the fracking itself. It's actually when you frack a well and you're pulling out water, you get lots of you're pulling out oil, you get lots of water to come out also, because there's water trapped in the rock, and also then you have all the drilling fluid and all the water that you put down for the fracking that you have to get out. That has to be disposed of. They dispose that down, they dispose that water into very deep disposal wells, way, way, way below the water table, into cracks in the rock. Cracks in the rock. That should mean something to you. What are cracks in the rock? They're faults. So they're actually disposing the water into faults. And every now and then it appears that the faults get lubricated by the water that goes down, and that's what causes probably most of the earthquakes that are associated with the fracking. And although there are some places where fracking seems to have actually induced earthquakes itself, most of it is due to the water disposal. Now there are, I don't know, 60,000 or 80,000 or maybe even 100,000 wastewater injection in the United States. Fewer than 1% of them have ever had induced earthquakes associated with them. Mm-hmm. So it's very hard to figure out which wells are going to have induced earthquakes and which aren't. But there are some that definitely have induced earthquakes.
Yeah. Excuse me. I'm a geophysicist. I worked in the oil industry for 25 years on shale plays. I have two things to say. First of all, when we inject used water in the ground, we are not injecting it in falls, we are injecting it in pores of the rocks. And what's happening is that sometimes companies which are not very ethical, small companies, are injecting in wells they don't, for which they don't have enough data. And then they can hit a fall by accident.
Right.
So normally what you do is a seismic survey, and you look at a place where you have high porosity, deep, and no faults, and that's where you inject the polluted water.
Right, but yeah. the faults, particularly if you have steeply dipping faults, are just not going to be imaged well at all on the seismic surveys. I mean, that's one of the problems, and probably why they accidentally hit faults when they weren't expecting it.
Well, it's not so deep, when the seismic can see the faults, but the problem is that sometimes they inject in all the existing wells, and they don't pay the money to make a seismic survey, and when they don't have seismic, and they don't know where the faults are.
Right.
That should be totally outlawed. I mean, it's disgusting. Another thing is my point of view on earthquakes from with fracking is that often they don't create earthquakes that wouldn't exist without it. They just start an earthquake earlier. They release stress in the earth earlier than if we didn't inject anything. Then in a way it can be good, because you frack rocks, you inject water, you create an earthquake, and the earthquake is on the Richter scale maybe an earthquake of magnitude 4, let's say. Yes. If you didn't do that, maybe 50 years later you would have an earthquake of magnitude 6, because the stress is building up.
Okay, so you're half right here. The problem is that the amount of stress that's relieved, or amount of seismic moment that's relieved in a magnitude 4 earthquake is nothing compared to what's relieved in a magnitude 6 earthquake. I mean, there's been this notion, Hollywood loves the notion that you can set off a small earthquake and somehow prevent a big earthquake from occurring, but that's just not the way it works. When we do the energy calculations or the seismic moment calculations, which are really stress budget calculations, magnitude 4s just don't relieve the stress that you relieve on a magnitude 6. Because a magnitude 6 now you're talking about something that's maybe 10 kilometers by 5 kilometers on a side is the area that has the slip. In a magnitude 4, it's like 1 kilometer by 1 kilometer on a size. So you can't relieve the
enough. You don't relieve enough. Okay.
That prevents the stress being relieved in the whole picture.
Okay, thanks.
But you are absolutely right. You're right about advancing the time. Maybe if they hadn't injected the fluid, there would have been an earthquake there 100, 200, 500 years, whatever, at some time in the future. And that by injecting the earthquake, there was a little excess concentration of stress, and they caused the earthquake to occur now rather than at some point in the future. Yeah, that is a possible idea.
Thanks.
Okay, we have one other question in the chat, but I'm going to leave it in the chat. It's about possible tsunami activity on Cape Ann, but I think our time is up. And so I just want to thank John for a real earth-shaking talk.
Thank you, John.
Thank you. You take care, guys.
Have a good night.
Thank you very much. Great questions too.
All right, excellent. I'll stop recording.